Hello, I am Devani Patil, Assistant Professor in Arihant College of Arts, Commerce and Science, Camp Pune. In last video, we discussed about the assembler. In that video, we discussed the introductory part of the assembler, how assemblers are useful for the system programming and how assemblers are the essential component for system programming. So just introductory part of the assembler, that is an assembler is a program that converts assembly language into machine code. So assembler's main function is to convert the assembly language program into machine level language. It takes the basic commands and operations from assembly code and converts them into binary code that can be recognized by a specific type of processor. Assemblers are similar to compilers. There is a functionality of the assembler and compiler is a little bit same. So, assemblers are similar to compilers in that they produce executable code. However, assemblers are more simplistic since they only convert low-level code, that is assembly language, to machine code. So the function of assembler is, in short, it converts the low-level language into machine-level language. Since each assembly language is designed for a specific processor. As per the specification of your processor changes, there are some changes available in assembly language also. But these changes are not huge changes. There are only some changes are here done as per the specification of your processors. Compilers, on the other hand, must convert generic high-level source code into machine code for a specific processor. So, assembler convert the low level towards the assembly level, and compilers are also doing the same thing but in a some short extent. This is the diagrammatical presentation of the assembler. Assembler take input from source program which is written in assembly level language and convert that input into the output format as a target program. Whenever you are writing any source program, that source program is converted into assembly level language or low level language with the help of assembler. So, your source program is input for your assembler. Whatever the changes done from the assembler into the source program, those changes are recorded by the assembler into his databases. So, you will get the exact record of the which source program is when lastly updated and who is the user. According to this, the assembler keep all the records into database of both files, that is input and output. Assembler converts source program into the target program, that is a machine language equivalent program. This conversion is happen with the help of some assembler directives. So these assembler directives are nothing but some statements or some special commands which perform their task according to the user requirement. So advanced assembler directives, these are the statements that direct the assembler to do something. As the name says, it directs the assembler to do a task. So, which directive you are using, according to that your assembler will be work. The speciality of these statements is that they are effective only during the assembly of program, but they do not generate any code that is a machine executable. It means that whatever the directives, assembler directives you are using, that are useful for the conversion of that statements as per the requirement, but they will not generate any type of machine executable code. The assembler directives can be divided into two categories, namely the general purpose directives and special directives. For some special cases, you can use special directives, and for the normal use, that is the simple conversions, you can use general purpose directives. There are so many directives are available in the advanced assembler directives. So these directives are classified into the following categories based on the function performed by them. So each and every directive having their own functions, and according to your requirement you have to decide which assembler directives you have to use. So the categories of the advanced assembler directives are simplified segment directives, data collection directives, segment directives, macros related directives, code level directives, scope directives, listing control directives, and miscellaneous directives. So all these type of directives you can use whenever you want to perform any special task with the help of assembler. So these directives will help to assembler to direct the assembler to do a task. Some advanced assembler directives are, I am listing here, EQU. You have to just use these keywords EQU. Assign a value to symbol that is equal. So the simple equal symbol is work as, or EQU assembler directive will work as a equal symbol. Next is ORG, that is origin. Sets the current origin to new value. This is used to set the program or register address during assembly. For example, ORG0100H tells the assembler to assemble all subsequent code starting at address 0100H. So this is the origin value of your assembler directives. Next is the DS. Defines an amount of free space, that is the define space is a DS directive. Here no code is generated. This is sometimes used for allocating variable space. Whenever you are declaring any variable, and that time you have to first create a space for that variable. So how will you create the space? With the help of this DS assembler directive, you can create or define a space to your variable. So this directive, this assembler directive is a define space, that is a DS. Next is a ID. Sets the PIX identification byte, that is the how much identification bytes you are allocating for a particular variable. Next is include. Loads another source file during assembly. This allows you to insert an additional source file into your code during assembly. Included source files usually contain common routines or data. By using an include directive at the beginning of your program, you can avoid retyping common information. So, you can add a new file or include a file into a program. Next, fuses. Fuse configurations can be and, that is, you don't have to use the word fuses, but instead of that you can use a symbol and together on a single line and or spread between multiple lines. So whenever you want to create or combine the lines, you can use this assembler directive. Next is the if. With these directives, you have to give some expressions, that is the conditional expressions you have to put here. If expression assembles code if expression value to true, then the expression is what will be the result if the given condition is true, and if the condition is not true, what will be the next expression that you have to specify here. If not expression assembles code if expression evaluates to false, means whatever the expressions you are defining in if expression, if that value will be false, then what will be the expression that you have to define in if not. Next is else. If and if not expressions are useful only the value is true or false. But is there any another value, then you have to use the next assembler directive, that is the else. Assembles code if a preceding evaluation is rejected. Next is end if. Whenever you want to come out from a looping statement, that is the expressions given in if directives, you can come out with the help of this advanced assembler directive, that is end if. Ends the conditional evaluation. Whatever conditions you are expressing in the if not, else, you want to stop those conditions, you have to use the assembler directive, that is end if. Whenever you are using end if, automatically you will go to the end of the conditional evaluation. Next is a reset. Sets the reset start address. This address is where program execution will start following a reset. A jump to the given address is inserted at the last location in memory. After the PIC is reset, it starts executing code at the last location. Means in the reset, whatever the value, counter value you are giving from that location, your execution will be again start. So after the peak is reset, it starts executing code at the last location, which holds the jump to the given address. Reset is only available for PIC 16C5X chip. So this is available for this specific chip only. Now design of a assembler. How you have to make a design of assembler. General design procedures specify the problem. So you have to use some steps to design an assembler. Specify the data structure for that assembler, whatever the required. Then whatever the data structure you are specifying, you have to define that data structure. It means that suppose you want to declare three variables, specify these three variables, then define those three variables, because you have to create the space for those variables. Then specify algorithm, that is the which type of register you want to use, what is exactly mathematical operations you want to use, that you have to write in a algorithm. So after specifying and defining a data structure, you have to specify a algorithm. Look for modularity, that is the which modularity you want to use. For the addition, there is a one modularity. As per the requirement changes, your modularity will be changes. Suppose you are using more than one modularity in your program, then you have to again specify that particular data structure. Again, you have to define that data structure for the different module. It means that for the second module, you have to repeat from step 1 to step 5. Then what are the objectives of assembler? It generates instructions. Assemblers generate instructions with the help of directives. Assemblers evaluate the mnemonic in the operation field to produce its machine code. Assembler create their own, not their own, but mnemonics in operation field to produce a machine code. You can create a machine code as per your requirements. Find the value of each symbol, process, literals. That is suppose you want to declare a variable, you have to specify the variable, and vice versa. If you are specified a variable, you have to use that variable. So find the value of each symbol, process, literals. Process pseudo operation. It creates the pseudo code and the operations related to pseudo code are created and executed. Data structure for design of assembler. Which type of data structure is used in the design of assembler? Mainly, there are 7 types of data structures are used in design of a assembler. First one is the MOT, that is the machine opcode table. Second, segment register table, SR tab. Third, stored segment register table, that is the STRT. Symbol table, SY tab. Forward reference table, FRT. Cross reference table, CRT. Literal table, LT. We will discuss each and every data structure in the next video, that is the macros video. So these are the most important data structure mostly used in the design of assembler. Rather than these, there are so many data structures are created by the system for design of an assembler. Design of assembler is classified in mainly two parts, that is the analysis phase and synthesis phase. So, what is the analysis phase? In the analysis phase, it reads the source program and splits it into multiple tokens and constructs the intermediate representation of the source program. As the diagram shows, that analysis phase is converts the source program into intermediate representation, means half portion of assembling a particular code is completed here in analysis phase and remaining part is covered in the synthesis phase. So analysis phase reads the source program and split it into multiple tokens and constructs the intermediate representation of the source program. In this phase, main source program is decomposed into multiple parts. We can say here multiple tokens, and these tokens are not separated. These tokens are bundled into an intermediate representation. This intermediate representation will be the input for the next phase, that is the synthesis phase, and also checks the indicates the syntax and semantic errors of a source program. It collects information about the source program and prepares the symbol table. Symbol table will be used all over the compilation process. This is also called as a front-end compiler. because once a source program is given for the execution, then that time it is the just of starting phase of execution of your program, this is the starting phase of compilation of your program. So you can easily say that your program is under executable stage. So this is the front end of the compiler. Now what is the last end or the back end of the compiler? Back end of the compiler is a synthesis phase. As in the synthesis phase, it is take input from the analysis phase, which is a intermediate representation. This intermediate representation is converted into the target program when it undergoes the synthesis phase. So what is the synthesis phase? It will get the analysis phase input, that is a intermediate representation and symbol table, and produces the targeted machine level code, that is the some assembly level directives are used here in synthesis phase, and this happens at the back of the screen, so it is mostly called as the back end of the compiler. Both the analysis phase and synthesis phase we combined here in this diagram. Half portion of this intermediate representation, that is covered in the analysis phase, and half portion is covered in the synthesis phase. Once source program is handled by the assembler in analysis phase, it is constructed, that is the errors are checked in this phase. If there are any type of error, it is shown on the screen, and if again it is error is handled by the user, it again go for the construction. That is the only 50% of work is done here in analysis phase, and it shows on the screen, that is the how exactly line by line compilation is happen. So it is a front end of your compiler. Once errors are checked and analysis phase send the inputted source program into the construct format, and the symbol tables with the help are created. So that output is considered as an input for the synthesis phase. But not only the code is sent towards the synthesis phase. With the help of intermediate representation, what is intermediate representation here? That is the splitting of your source program into small components is constructed into an intermediate representation, and that whole bundle is sent towards the synthesis phase as an input. But not only the splitting of the source program, that is the decomposition of source program is sent towards the synthesis phase, but the symbol table related to that source program is again sent towards the synthesis phase. Now this happens by the assembler, compiler, so it is a back end of the assembler or back end of the compiler. In the synthesis phase, when whole procedure happens, it is your source program is converted into the machine code or into the target program. So this is the combined working or the combined operation of analysis phase and synthesis phase. Here are some references I am using for this video. Thank you.